Okay, so verifying trigonometric identities. That is the whole lesson today. A memorable one of that. Right? Verifying trig identities. First, by identity, and I spelled that wrong. Identity. I have to fix that. By identity, take that out. It's an equation that's always true. And we actually were already dealing with some identities. Right? We're dealing with these are identities. It means that it doesn't matter what the U is. This is true. Always true. So today we're going to have things that are not of the fundamental identities that we're going to have to show are identities. So verify, which means to show by use of some algebra and by the fundamental identities, which were a part of the last lesson. We try to show that in this equation, what's on the left is actually the same as what's on the right. So we're going to try to make both sides be the same. That's what verifying trig identities is. All right. And now these I showed you at the end of the last lesson. It comes from this lesson, but these are just basic guidelines. The thing about verifying trig identities is that there's many different ways to do these. And some of you surprised me with the way you looked at it, and you still get it right. Right? There's not just one solution. In fact, all of the homework problems, there's no answers in the back of the book. It just says answers will vary. That's it. So you just have to try to be creative. But these are the basic guidelines. The first one is work with one side of the equation at a time. Usually you're going to work with the more complicated side and see if it simplifies. You know, maybe just by doing that, it'll look like the other side and you're done. Sometimes you don't. Sometimes you have to work a little bit on one side, a little bit on the other. Okay, look for opportunities to factor, add fractions, square a binomial, or create a monomial denominator. All things that except the square a binomial, I'm not really quite sure where that comes from, but the rest of those we did in the last lesson. So it could become part of what we do. Look for opportunities to use the fundamental identities, right? Especially the Pythagorean identities. You know, you can always jump from sines to cosines, secants to tangents, cosecants to cotangents, and that is useful. And then sometimes just make everything sines and cosines, because all of the 6 could be written in terms of sines and cosines. And sometimes you'll see some simplification that's possible when it wasn't before. And then the last one, always try something. I mean, if you try something and it doesn't work, go back and try something else, right? If you tried, there should be some evidence that you tried something, not like a blank piece of paper. I tried. Really? What'd you do? I mean, that's just the nature of it. It's very common in this kind of thing that you might start and you get stuck and say, that didn't work. Let me see if I could do it a different way. So in a way, this lesson in particular, kind of like math induction did, when we did that part, you know, how do you prove something is true for all n? It tests a little bit different way of thinking than most of the rest of the lessons that we get here. So again, I don't have that many examples here, but they're mostly the ones in the book. Some of them are also the checkpoints. But to verify this identity, we need to make the left look like the right. And rule number 1 is, probably you're going to work on the side which looks more complicated. Okay, Thomas, you awake there? Okay, which clearly would be the left-hand side. Okay, what kind of substitution suggests itself here? Well, secant squared minus 1. That ought to make you think of Pythagorean identity, right? I mean, if we look at that, secant squared minus 1 would be equal to what? Tan squared, right? So, you know, we can use that. Tan squared theta over secant squared theta. Okay, still not where we need to be. What else could we do? How about we turn these into sines and cosines? Because I know that tangent is sine over cosine, and secant is 1 over cosine, so there could be some canceling that goes on if we just make it all sines and cosines. Right, so this is sine squared theta over cosine squared theta, and that's all divided by 1 over cosine squared theta. And then if you don't see it, since both the numerator and the denominator are being divided by cosine squared, right, you could just cancel those, and the answer will be sine squared. If you're not comfortable with that, you should remember that if dividing by a fraction is like multiplying by the reciprocal, right? So this is sine squared divided by cosine squared times cosine squared over 1. And then they cancel. And there's your answer. I mean, but you could have gone a different way. I mean, you could have said, let's make this first one secant squared over secant squared. That could be the first term. That's 1. And then minus 1 over secant squared. That's cosine squared. So we would have 1 minus cosine squared sine squared. Totally different way to go. Same answer. Okay. So any substitution suggests itself. We can't do that. Yeah. Sine plus cosine does not equal 1. Sine squared plus cosine squared equals 1. So yeah, you could substitute the whole numerator as 1. I mean, that is definitely the way you'd want to go here. 1 over cosine squared theta secant squared theta. Then what? To what? Yeah, I mean, this secant squared, which is already in the denominator, is 1 over the cosine squared. So it's going to cancel with the cosine squared. Whether you show it like in the denominator, cosine squared divided by cosine squared, or whether you just flip it up there like that. In either case, they cancel, and the whole thing is 1. But the key is this equals 1 because of that. You got to always think of Pythagorean identities. Okay, which is the more complicated side here? The right side. And I think this was something, it was like a homework problem that we had, or one of the examples that we went through, right? How did we simplify the right-hand side in the last lesson? We had to find a common denominator, right? And you had to multiply this term by 1 plus sine alpha, and this was times 1 minus sine alpha, and that was divided by 1 plus sine, 1 minus sine. So in the end, it would look like this. 1 plus sine alpha. Let me not do that. Um, 1 plus sine alpha plus 1 minus sine alpha divided by 1 minus sine alpha, 1 plus sine alpha. Right? That's just making a common denominator. Okay? Now we got some canceling. It goes on in the numerator. Right? These two cancel. So the numerator looks like 2. which is good because look on the left-hand side, there's a 2. So, okay, we got the 2. And then what is 1 minus sine times 1 plus sine? 1 minus sine squared. But 1 minus sine squared is cosine squared. And now looking at the left-hand side that we're shooting for and the right-hand side that we've got so far, what's the last change? I mean, cosine squared in the denominator is secant squared in the numerator. So that is 2 secant squared alpha. So I'm just copying this in the order that they had it in there. We've actually used these already. But, you know, besides having a substitution for sine squared plus cosine squared, we have a substitution for sine squared for cosine squared. Right? You can solve by solving for any one of these terms. You have a substitution that sometimes will help. And sometimes the reason you do it is so that you create a difference of squares, right? None of these have difference of squares involved, but all of these do. And that sometimes is helpful. So you just keep an eye on whether a difference of squares factoring might be useful, right? 1 minus cosine squared, 1 plus cosine, 1 minus cosine, 1 minus sine squared. Yeah, this one is secant plus tan, secant minus tan. Secant plus 1, secant minus 1. Okay. So make the left-hand side look like the right-hand side. Work with the more complicated side first. Which side do you suggest we start with? The left side? Okay. Any suggestions? Okay, we try to FOIL. So if we FOIL this, we're going to get tan squared x cosine squared x minus tan squared x plus cosine squared x minus 1. What's a good next step? Yeah. Okay, so he's saying, how about instead of that, we would just substitute tan squared plus 1 is secant squared. Okay, then what would you do with the cosine squared minus 1? Negative sine squared. So, I mean, I would have gotten to this step right here and said, I'm not sure what to do next. Let's go back to the drawing board and then maybe look at what you did. I think that's what we should have done. We should have said, oh, what happened there? There it is. Right, so this would have been secant squared x, and this would have been negative sine squared x. Okay, how does all that turn into negative tan squared x? Right, secant squared is 1 over cosine squared, so that's negative sine squared divided by cosine squared. And that is negative tan squared. You know, sometimes if we did it like we did the first time and it looks complicated, I mean, it's not saying that we could not have made that work. We might have been. You know, I would call it a brute force method that keep trying and trying and trying, and sooner or later you get some cancellation and it actually does simplify. And some of you will do that. It'll be so much fun to grade your test. Try to follow what you did. Okay. So that's what we did this for. How about this one? Make the left look like the right. Which side would you think is more complicated there? The left? I would tell you that it is the left. The left is where we ought to be working. But, you know, I could understand if you thought, I don't see much difference in the level of complication here. The only thing is that if you got more than one term, then just the simple fact that this is going to be sine over cosine and this is going to be cosine over sine, and you're going to have to find common denominator, that will generally get you towards one term, which this is just one term, right? Two factors, one term. So let's switch to sines and cosines here. See what it looks like. Sine x over cosine x plus cosine x over sine x. Okay, what do I have to multiply? What is the common denominator? Sine x cosine x, right? So we're going to multiply by, this one will be multiplied by sine x over sine x. This one will be multiplied by cosine x over cosine x. Right, which this term then is sine squared. This is sine squared x plus cosine squared x in the numerator divided by sine x cosine x. Is that getting us there? What's the next absolute must-do substitution? Sine squared plus cosine squared equals 1. So you just substitute for the numerator. 1 over sine x cosine x. Okay, well, we need it to look like secant x cosecant x. Are we there? Yeah, I mean, 1 over sine is cosecant. 1 over cosine is secant. So yeah, that's it. I'm not sure why I put that one in there, but that's okay. Again, okay, if we're going to do the same thing with this one, probably we're going to work on the left-hand side. What am I going to do the left-hand side? Change cosecant, right? So that's 1 over sine minus sine x. Okay, in order to combine those, what do I have to do? I need to have a common denominator, right? So this one's got a denominator of sine, this does not. So we're going to multiply by sine over sine. And now they have a common denominator. So you put them together. That will be 1 minus sine squared x over sine x. Is that right? Cosecant, 1 over sine. Sine x, sine over sine. 1 minus sine squared is, oh, okay, I got it. So then what's the substitution? Yeah, 1 minus sine squared is cosine squared, right? 1 minus sine squared, cosine squared. And notice that this is supposed to be the product of two different functions. So you're going to have to take that cosine and split it up into a cosine times a cosine. It'll look like cosine x divided by sine x times cosine x. Right, there's your cosine squared. Right, and this is not adding or subtracting. It's not like you got to put a sine x there. Right, just one sine x and there it goes. And cosine over sine is cotangent, and the cosine cosine. Done. Okay. Which side does it look more complicated? The right side? You know, in these, I've cut these out, you know, their direction. Most of them in the example said, this is one where you work on the right first. This is one where you change all sines and cosines. I think this is the one that they said, work a little bit on the left and a little bit on the right. So we don't have to make the left look like the right or the right look like the left. We could make this look like something and then make this look like the same thing. That would be good too. Okay, let's see. How about we work on the left first, right? The left looks like secant and tangent. Maybe we could do a 1 over cosine plus sine over cosine. Okay, that looks okay. So then that is 1 plus sine x over cosine x. We didn't even have to find a common denominator. We already had it. Okay. What's that? 1 minus sine x is cosine x? No. No, but you know what I'm thinking here is, what if we multiplied this one by 1 minus sine over 1 minus sine? Because I can see that that side's got a 1 minus sine in the denominator. That would like introduce the 1 minus sine, and then it would give us 1 minus sine squared here. Okay, so let's try that. I don't think that's the way they do it in the book. But 1 minus sine divided by 1 minus sine. And that's going to be 1 minus sine squared. And this is cosine x, 1 minus sine x. Okay, but 1 minus sine squared is what? Cosine squared. So that is cosine squared x divided by cosine x, 1 minus sine x. And notice that we've got to get to this. So there's only one more step. You got a cosine denominator, you got a cosine squared here. One of the cosines cancel, and then you've got that. So cancel one cosine out of that. And now we've got that. We got cosine x over 1 minus sine x. I mean, did anybody think when we had this 1 plus sine over cosine, right? What if you had 1 plus sine over cosine equals this cross multiply, right? A fraction equals a fraction, just cross multiply. 1 plus sine times 1 minus sine is 1 minus sine squared, cosine squared. That'll work. So definitely there's more than one way to do these things. Okay. Any suggestions? Cross multiply, because I just said that? That's clever. Well, you know, if we cross multiply, you know, it's not like we have the factoring of a difference of squares, because this is 1 minus sine, and that is 1 plus cosecant. It's not going to be the obvious simplifying. cotangent squared times sine. You have one squared term there for which you could substitute using Pythagorean identity. Which one is it? The cotangent, right? I could substitute for the cotangent squared. What would it equal? Cosecant squared minus 1. So just try to picture whether that looks like it would get you anywhere. If I put in a cosecant squared minus 1 here, then how would that factor? Cosecant plus 1 times cosecant minus 1. Well, you got a 1 plus cosecant in the denominator, so yeah, that's going to cancel. So I would do that. Substitute 1 cosecant squared theta minus 1 over 1 plus cosecant theta. And this is cosecant theta plus 1 times cosecant theta minus 1 over 1 plus cosecant theta. Did we do everything all right? Cosecant squared minus 1. Okay, now we cancel this. So we got cosecant theta minus 1. Now that's still not that. So I think this is the one where we work a little bit on the left and then we work a little bit on the right. Let's work a little bit on the right. What could we do to simplify that? 2 terms in the numerator, 1 term in the denominator. Split them up. Right? This side would be 1 over the sine minus sine over the sine. And 1 over the sine is cosecant. And the sine over the sine is 1. So we worked a little bit on the left, got it to this point. We worked a little bit on the right, and it's the same. Verified. And then these examples, they say from calculus. I'm not quite getting it, but they're not that tough. I mean, you're going to try to make these things look the same. The more complicated side would be on the right. What could we do? Right? Factor. There's a common factor, which is what? Tan squared. So factor the tan squared. So you've got tan squared x, and what's left in the parentheses? Secant squared minus 1. Okay, but don't we have a substitution for secant squared minus 1? Secant squared minus 1 would be tan squared. So that's tan squared times tan squared, which is tan to the 4th. And I think the other one is similar in that there's not, all you're really doing is factoring here. And it looks like there's been some factoring that's done already, but there's still something you could take out of the expression in the parentheses. What's the common factor? There's 1 cotangent, right? So this would look like cosecant squared x cotangent x times 1 plus cotangent squared x. All right, just factor out the cotangent. And then what is 1 plus cotangent? 1 plus cosecant squared. So this is cosecant squared x times cotangent of x times cosecant squared x. And then these two are cosecant to the 4th x. Done. Okay. That was it, verifying identities. And what we do with next class, the next lesson is solving equations. And the reason why it's here, I mean, we've solved some equations. We've solved right triangles. We've even done the law of sines and cosine stuff. But in these equations, we're going to need these identities, right, to do it. So there's a few. First few should be pretty easy. Remember, there are no answers in the back.